Good morning, good afternoon, or good evening, wherever or whenever you happen to be viewing this. An important tool of data science is statistics. Yet you have probably heard a quote that exclaims something to the effect that there are three types of lies in the world: lies, damn lies, and statistics. So if data science is going to leverage the power of statistics as a tool, you're going to need to get a feel for how statistics can be used to lie, and how to understand the truths a data scientist might be communicating to you. Gaining some insights on that problem is the goal of this section. As noted in the title, this section is going to come at you in three parts. In the first part, we will address the power of statistics to persuade, or how to lie with statistics. In part two, we will look at the basic statistical forms that one needs to understand if you are going to tease out some truths using statistics. In the third part, we'll make a foray into correlations. This will present us with a great opportunity to discuss what it means for something to be scientific versus statistical. These two concepts are often confused in the press, and if data science is going to be a science, then we must make certain to include the scientific method in our approach to understanding data. That is, if our understanding of the data is to be scientific. Before proceeding, I would like to take a moment to thank the Mavo Institute for giving me this opportunity to speak with you. The Mavo Institute is the brainchild of Martin Vonderheiden. I encourage you to take a moment to check out the Mavo Institute website as well as the team's profiles. One of Martin's key hopes is to tap experienced experts to address topics or problems at hand. As such, the team behind this presentation also includes John Murphy, a practicing tenured digital media executive, and myself, Dr. Paul Fielding. With that said, let's take a look at data science as statistics, lying with statistics, discerning truths with data science, and what it means to be scientific. Data science as statistics. This section is not intended to make you into a statistician. That takes years of schooling and practice. Rather, we hope to give you a feel for why statistics is important to data science. Likewise, we will look at the power of statistics to persuade and some classic techniques for lying with statistics. We will then look at what goes into a real statistic. The goal of this section is to help you gain some insights on what you need to know if you're going to tell the difference between someone that is baffling you with BS versus someone who is honestly working to tease out truths for you from a tsunami of data. We need statistics to help us sort through the fog of data. Simply put, our brains are downright horrible at processing data. Our minds often trick us into believing things that simply are not true. For starters, we often think our limited view of anything represents the entire world. That is simply wrong. Yet, if we happen to get a look at all the data that represents the larger world, our brains are often overwhelmed and we simply cannot see the forest through the trees. Even when we try to collect data, our samples can be influenced by things we are not aware of. When does our sample represent the larger group? And when does it not represent the larger group? Temporal effects also distort our perceptions. An example of this might be seen in, say, shopping for puppies. The first puppy we see is the best one, and we tend to compare all other puppies to that first one. Or by contrast, sometimes recent events distort our perception of the past. We tend to think the current weather is indicative of some sort of trend. Or when in an argument with our significant other, we might distort the current annoying behavior by saying, "You always." Both effects, primacy and recency, distort our perceptions and can keep us from making good decisions. Additionally, we judge the world by what we see, and we often fail to take into account what we are missing. The classic example of this is when people say the full moon correlates with clear skies. From our personal experiences, we think we have a lot of data to back this up, but we are forgetting that we only see the full moon when the skies are clear. And then we often find data to support the decision that we've already made. Consider a new date we are enthralled with versus the ex. We find lots of data to support the position that the new one is so much better than the ex. Then, when the new one becomes the ex, the data seems to change. Clearly, Data is not always gathered objectively. Simply put, our brains are often beat down by big data. It is downright dangerous to make decisions from raw data sources. Thus, we need statistics. The problem here is that because of our brain's weaknesses, it becomes easy to suck people in with pseudo statistics. The old joke is that 87.3% of people will believe almost any statistic quoted to them. Things that sound like a statistic have a power to persuade for many reasons. People assume numbers are objective, precise, accurate, and unambiguous. We assume that these numbers are backed by careful, honest research that is reliable and reproducible. We buy in and follow the leader of this dance because it simplifies what overwhelms us. It makes us feel smarter or better for knowing this new truth. And then we use inferred justification to support the other person's lie. We make excuses for the lie by saying to ourselves, if this statistic is true, then other stuff in the world also makes sense. Lastly, if it confirms what we want to believe, then we believe it because, well, it confirms what we want to believe. By the way, I bet you already knew that this is indeed a bogus statistic. I bet you already knew that because there are some not so subtle telltale signs. Specifically, this statistic is not objective in any manner, shape, or form. It overwhelmingly supports only one point of view, and there's not much room for debate here. There are no competing hypotheses that are reasonable. There is no research cited to support this statistic. And even if I did, say, cite the groundbreaking study of Dr. Schwabelmeyer at Leipzig University, is it reasonably possible for one to run an experimental test to confirm this statistic? If the answer is no, then the statistic is not scientific. But more on that in part 3 of this module. It overwhelmingly simplifies a vast body of experiences you may have had. It lets you think that you are smarter than others for probably having already suspected this. Likewise, if this statistic is true, it lets you infer other things about how other people may use statistics to deceive and incite, which may be something you might already want to believe. And perhaps politicians and doomsday sayers and others might take advantage of your desire to want to believe. By the way, I'm not trying here to pick on politicians or doomsday sayers or such. As an exercise, take some time to ponder what other groups have a reputation for deceiving people with statistics. Trust me, there are a lot of them out there. The bigger truth here is that because of how our brains so easily get lost in the fog of data, we can easily be tricked into believing things that sound like they could be a statistic and that sound like they are scientific. Unfortunately, to manage our lives and function in our modern society, we need to be just as fluent in statistics as we might be in reading and writing. Or as H.G. Wells pointed out, statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. What distinguishes a truth communicated by a data scientist is that to discern that truth, the scientist applied processes, methods, practices, and standards to the study of the problem at hand. We begin by looking at the question being asked in the context of the environment being addressed. At this stage, the John Dewey quote often comes to mind that a problem well put is a problem half solved. When doing this, we must consider our model that we are using for the world in which the problem exists. Are there hidden biases, dependencies, or other factors that we are not taking into account? Have we somehow predetermined our answer by how we have structured our model or our view of the world? What are the competing theories or ideas that we are also considering? And yes, there must be competing ideas, theories, concepts, or options that are being considered. These competing concepts must also be reasonably plausible, or we have again stacked the deck against finding the truth. Lastly, we must consider how we will collect the data. Will the sources be able to create a bias? How will we know the collected data is relevant? A data scientist considers all these things even before the first bit of data is gathered or analyzed. Once the data is gathered, the data scientist may begin to summarize the data using statistical tools. Every statistic has several components to it. A statistic is not just a singular number. First, there is the sample size. This sample size also may be given in the context of the total population being considered. Then we need to know what type of distribution best represents the data being discussed. Additionally, a statistic is often accompanied by a mention of the variance or confidence interval. This basically tells you how much wiggle is there around the number being used to represent the data. Depending on the statistic and how the data was collected, these numbers help to define the significance of the answer being represented by the data scientist. The shape of things to come. Now, every child learns how to work with shapes long before they try to add 1 plus 1 to get 3. Okay, we're going to shift gears here a bit. We've established that people can make your brain numb with numbers, and effectively, with enough pseudo-statistics, they could get you to believe that 1 plus 1 equals 3. But if you take the simplistic view of a child and work with the overall shapes of things, heck, our brains are much better at working with shapes than numbers. Then, without a lot of complex math, you can get a pretty good feel for what fits into what makes sense, and what is nonsense. In the next module, we will familiarize you with 4 key shapes. The idea being that if you can be conversant in or manage situations that lend themselves to these 4 key shapes, you will probably know more about the nature of statistics than most people around you. The first of these that we will consider is the binomial or Bernoulli distribution. This tool is most useful when discussing option-type questionnaires or yes-no surveys. Then we will familiarize you with the normal distribution or bell curve. This is most useful for measures that vary equally about a central point, being the mean or average value. This leads us to the Poissonian distribution. Basically, our concern here is that when data gets bunched up against a limiting value and the average value does not equal the most commonly occurring point, how do you work with that? What do you need to be aware of? Lastly, we will look at the Pareto chart, a handy tool for identifying what is mostly responsible for the issue you are studying or trying to solve. Where do you focus limited resources, and what can you expect to accomplish? By the way, there is actually a 5th key shape that we need to discuss, the scatter diagram and correlations. We will not get into that in the next section, but we'll get into that in the section following the next section. That is, in part 3 of this presentation, we will discuss correlations and what it means for something to be scientific versus statistical. If you are familiar with these shapes and understand the significance of them and how to work with them, it will be a lot harder for someone to convince you that 1 plus 1 equals 3. And if you are presenting some results, you may be more effective at communicating the significance of your results by using an understanding of these shapes to communicate with your audience. I look forward to studying these shapes with you in part 2 of this module on data science at Statistics.